So that's 6-2 today in Advanced Algebra 2. Today we'll talk about inverses. First, before we talk about an inverse, we need to refresh our memory what a relation is. Relation, quite simply, is a set of ordered pairs. A relation is just a plain old set of ordered pairs. So if a relation is a set of ordered pairs, an inverse, quite simply, I'll just get straight to it. An inverse is a reflection over the line y equals x. X and y switch places in an inverse situation. So if this is a relation, which it is, Q right here, isn't that a set of ordered pairs right here? And they want us to find set S to be the inverse. Well, we definitely know it's a set. All we got to do is take those particular ordered pairs and switch x and y around. So if the first point is 1, 2, the second one would be 2, or the first one would be 2, 1 in its inverse, and etc. Separate them with commas, put in parentheses around the particular ordered pairs. An inverse is a reflection over the line y equals x. You can see back to the original example up here. It's like for a real life guy, when would you need an inverse? Well, it's like when you're converting, like from Celsius to Fahrenheit or backwards from Fahrenheit to Celsius. Those are like inverse operations, and other things changing from meters per second to miles per hour and stuff like that. It's all about inverses. So here's what we want to do. They say graph the ordered pairs in relation A here in example 2. Let's plot those 3 points. I'm a geometry guy. I don't believe in just plotting 3 points. If you're going to plot them, let's put some labels on them. Let's call this one X, this one Y, and this one Z, so we can really see what's going on there. And then plot them. 2, 1, put an X next to it since that's what we called it. And then plot those other 2 puppies. And then take a straight edge and connect them together and make a polygon out of them. X, Y, and Z. They ask us what kind of figure do you get when you connect them together. Obviously, it's a triangle. Anything a little more special about that you know? It's a right triangle because one side is vertical, one side is horizontal. You know they're perpendicular to each other. So this is a right triangle. Then they say find the inverse of this relation. Well, if this is the set of ordered pairs right here, I will find the inverse. They already put the set brackets for me, so I just got to pull the old switcheroo on these. Switching x and y around. An inverse is a reflection of some relation over the line y equals x. Then graph those. So if this was x, y, and z in that order, you may have seen these, you may not remember, but we'll change x to x prime. That's like with an apostrophe next to it. We'll call this y prime, and we'll call that z prime when we plot them. Those are like the reflections of each other. Usually introduce the primes when you do some sort of reflection like that. And connect them together. That is also another right triangle. Right? These are congruent shapes. When you do a reflection, that's an isometry, which is a congruence transformation. Keeps things same size, same shape. The ABCDs are preserved. Angle measured between is collinearity distance. Great geometry refreshers. What I'd like to do, though, is actually graph the line y equals x as a dashed line. Y equals x. Is that horizontal, vertical, or oblique? Y equals x. Horizontal, vertical, or oblique? Y equals x. Horizontal, vertical, or oblique? It's oblique. How come? This is an oblique line because it has both variables in it. Is it in slope-intercept form? Is y all by itself on one side of the equal sign? What's the slope of this line? 1. What's the y-intercept of this line? Please graph that line as a dashed line. Y equals x. The most simplest line in the world is always the most difficult to graph. All right, you start at 0 on the y-axis, rise 1, run 1, rise 1, run 1, rise 1, run 1, dashed line. How are those two triangles, the red one and the blue one, related? Because they're inverses, how are they related? What have I kept saying to you about these? They do what to each other? Starts with an R. They reflect to each other over what? The line y equals x. They are reflection images over the line y equals x. They are reflection images over the line y equals x. Graphing equations and its inverse. So for these problems, let's graph the function, make a t-chart of at least 3 ordered pairs. Using the first t-chart, write a t-chart for the inverse, plot the ordered pairs of the inverse, and connect them. Use the dashed line, plot the line of reflection. One thing at a time. First, they want us to make a t-chart for this. Hey, we have knowledge. Not trying to insult you. Line, parabola, cubic, 4th power, 5th power. What's this going to look like? Line. First power, right? Let's make up some points in a table of values. Please make a table right here, then make an inverse table right below it. Okay? Whatever your equation is, make sure if it's a line, we put it in slope-intercept form and write it above this one. Seems a little ridiculous, but we want to do that. Write it above this table. This will be the inverse of that guy. Okay? One thing at a time. Make up whatever x values you want. They say 3. How about 0, 1, and 2? You down with those 3 numbers for x? If x was 0, y would turn out to be -5. Now let's see how good you are of understanding what a linear relation is all about. If x was 1, we'd put 1 in for x. You take 2 times 1 to get 2. Take away 5, what do you get? -3, right? Hey, time out. What was the rate of change from a -5 to a -3? Wasn't it a 2, right? That's what a line does. It's a constant rate of change. What's this one going to turn out to be? -1. Plot those points. Obviously, you can still just graph the line the way you're used to. You know the y-intercept's -5. You can rise 2, run 1, rise 2, run 1, rise 2, run 1. Take a straight edge, connect it together. Then grab a particular highlighter. I don't care which one. If you have like a pink one, choose that one because I'm using red. Red and pink are very similar, just to kind of coordinate with my colors. If you have a pink one, use the pink one for the first guy. Highlight this equation. Where's my highlighter? Whatever color you highlighted it, and highlight that line, that same color also. Highlight the line, whatever color you grabbed, and its equation, that color. Cool. Now let's do the inverse. Inverse is a piece of cake. Don't we switch x and y around? Right? Isn't that what we did in the front page? Inverse is just switch x and y around. That's why the table's so easy. So here's my y column. Isn't that all going to come over to the x column? -5, -3, -1. All right, just go one thing at a time. Then the x column is going to come into the y column, 0, 1, 2. Plot those 3 points. Then graph that line. Depends on how well you connect the dots together, because we only use 3 points. Try to be pretty accurate on how you connect the dots together. And then grab your second color highlighter, whatever color that is. Highlight the word inverse, that color, and then highlight that actual line, that color. Then keep that consistent on the next 3 problems. If your inverse was blue, keep highlighting it blue. If your inverse was yellow, keep highlighting it yellow, etc. Okay? They want us to graph one more thing, the line of reflection. What's the line of reflection? Y equals x. Just do it in pencil, but it's supposed to be a dashed line. Graph the line y equals x as a dashed line. Again, they should reflect to each other over this line. It depends on how accurately you connected them together, but all 3 of those things, the red one, the green one, and the dashed one, should intersect at one particular place. It's how well you lined your straight edge up if you made a little human error, but they should reflect over the line y equals x. Where they reflect at, in this particular case, is 5, 5. Check that out. 5, 5. Does y equal x? Yes or no? 5, 5. Y equals x on that one. Next, let's do it again. This linear, quadratic, cubic, what does that thing look like? Linear, all first power stuff. Is y all by itself? Nope, get y all by itself first. Y equals 4, correct? Think about it. Horizontal, vertical, or oblique? Horizontal. It's only got y's in it. So make up whatever x values you want in your first table. Sorry, I'm going a little fast. You need the tables. If I try to substitute x in up there, there's no room for x. There isn't even an x in the first place. That's because they're straight up telling you that y is how much? 4, 4, and 4. It doesn't matter what you got for x, y is going to turn out to be 4. Let's graph that. If you plot those 3 points, you'd go 0, 4, 1, 4, 2, 4. If you connect them together, shouldn't you get a horizontal line? And doesn't it go through 4 on the old y-axis? Then highlight your original color. Okay? I want to do a little bit of previewing for a second. This guy right here, the red line that I graphed, y equals 4, is he a function? How do you tell if a graph is a function? You just do one quick little test. How do you tell if a graph is a function? What test do you do? Vertical line test. Does that red thing pass the vertical line test? Yes or no? That's a function. Sound cool? This is a function. Let's do its inverse real quick. Don't we need to switch x and y around? So this whole column of 4s comes here, and the 0, 1, 2 goes over here. Just pull the switcheroonie. And then I'll graph it. Plot those points of 4, 0, 4, 1, 4, 2. Connecting those together, that's a vertical line, correct? That's a vertical line. The green one is the inverse of the red one. The red one was a function, correct? Is its inverse a function? Is the green one a function? Does the green one pass the VLT? No, it does not. So you can have a function, and its inverse could not be a function. Then graph the line y equals x in pencil. Those two, again, reflect to each other over the line y equals x. So we need these 4 problems to help us on the next page, so let's keep going. I know you get it. Number 3, line, parabola, cubic, 4th power. What do you got? Line, is he in slope-intercept form? Yes, he's oblique, so make 2 tables. One at a time. Pick whatever you want for x. I always pick 0, 1, 2 if I get a choice in a line situation. Now, if it was a quadratic, I would maybe choose something different. You know, if it was a square root function, I would definitely choose something different. 5, 6, 7. Do you see how the rate of change of all your y's went up by 1? Because wasn't that the slope? Graph him, highlight him. Here's our first guy, the red one. Is he a function? Does that pass the vertical line test? Yes or no? Yep, that's a function. Now let's graph his inverse of 5, 6, 7 over here, and 0, 1, 2 over here. So get that plotted. Should look here. What do they look like to you with just gut instinct? They look like parallel. Slope, 1 over 1, 1 over 1, 1 over 1. Slope here, isn't it still 1 over 1, 1 over 1? They got the same slope. There's the line y equals x. Do they reflect to each other over the line y equals x, though? Is the green one a function? Red one was the original. It's a function. This is its inverse. It's also a function. It could happen, right? You're a function. Its inverse is a function. Last one. Horizontal, vertical, or oblique? Oblique. It's got both x and y in it. one's interesting. Let's see what happens. 0, 1, 2. There's no such thing as negative 0, so you just put 0 in again. You get negative 1, negative 2. You graph that line, y-intercept of 0, slope of negative 1. Starts looking like this. I actually end up putting more points on there than the 3 when it's a line, because I could just keep doing my rise and run. Looks like that when you graph it. Do the old inverse, the old switcheroonie. 0, negative 1, negative 2, 0, 1, 2. Let's go green, because that's what color I want him to be in. So I got to plot 0, 0, which is right there on the red one. Negative 1, 1, which is right there. Negative 2, 2, which is right there. What the heck is going on here? Tell me about all them green dots. Where are they located? On the red line itself. So when you connect them together, you get the same thing, which I did, you don't have to do. It's the same thing, because graph the line y equals x. Does this red line reflect to itself, my bad, I didn't do it, over the line y equals x? With arrows on it, of course. The original guy and its inverse are the same thing. It's its own inverse. Weird. Next. The inverse of a relation will always be a relation. If you got a set of ordered pairs, if you switch x and y around, you're going to get another set of ordered pairs back. You start with a relation, it will always be a relation. But the inverse of a function is not always a function, as indicated right here. If I go back, how about I go forward? The inverse of a function, here's the red guy. That's a function. Its inverse was not always a function, correct? Just like on that second example that we did right there. Back, 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 back. Forward, 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 forward. So how do we determine whether a graph represents a function? You just told me that. If I gave you a graph, how do you know if it's a function or not? Use the what? The vertical line test. We use the vertical line test to see if a graph is a function. Well, if you graph a vertical line and we want to know about the inverse being a function, we don't even need to graph the inverse at all. We don't have to do that. If the vertical line test tells that a graph's a function, then if you reflect that over the line y equals x, the horizontal line test will let you know if the inverse is a function or not. So to determine whether an inverse is a function, we use the horizontal line test right there. So it says, with all of this, it says, tell whether the inverse of each function is a function. Explain your reasoning. Graph number 1. It's a function already. They told us so. This is a function. Doesn't he pass the VLT? Right? We don't care about that in these questions. They want to know, is the inverse a function? So you take the graph and use the horizontal line test. If you graph horizontal lines through this thing, would it intersect in more than one spot? What do you think? Yes or no? One spot, one spot, one spot, one spot, one spot. It looks weird right there. That's just, it's going to pass it there. Okay, I know that's new to us, but this does pass the horizontal line test. So what does that mean? Here's what it means. The inverse of f of x is a function because f of x passes the horizontal line test. The inverse of f of x, that's what this graph was, f of x. The inverse is a function because f of x passes the horizontal line test. The inverse of f of x is a function because f of x passes the horizontal line test. Try the horizontal line test on number 2. We know number 2 is a function. It passes the vertical line test. would its inverse be a function? What do you think? Yes or no? No. So we'll say no. The inverse of the parabola is not a function. Don't just say it's not a function, because I'll tell you what, that is a function. Its inverse is not a function, right? Its inverse is not a function because the graph does not pass the horizontal line test. That's the most difficult thing about this, is what to write down or what to say. That graph was a function. Its inverse is not a function because the graph does not pass the horizontal line test. Nice? So it says, go back to example 3. You don't have to flip it. You can flip your page if you want, but those are the 4 problems from example 3. Where example 3 was the previous page. It says, and examine the given functions. All of these were given functions, which are my, ooh, I screwed that up. The red ones, yeah, all of them were the red ones, right? Yeah. Red was the given functions. Which ones pass the HLT? This red one, does he pass the HLT? Yes or no? So, boom. This red one, does he pass the horizontal line test? The red one is a horizontal line, correct? This does not pass the horizontal line test. Does this one, the red one, pass the horizontal line test? Yep. Does this one, does the red one pass the horizontal line test? So, which ones pass the horizontal line test? 1, 3, 4. Out of those problems on the previous page, 1, 3, and 4 pass the horizontal line test. Which ones have inverses that are functions? Well, what would you think? 1, 3, and 4, the ones that pass the horizontal line test. And we actually have all the inverses graphed on those. Doesn't this pass the VLT? Doesn't this pass the VLT? And doesn't that pass the VLT? But the whole point of the horizontal line test is to say, don't graph the green ones. You don't need to graph the green ones. If the red one passes the VLT, it's a function. If the red one passes the HLT, its inverse is a function. So 1, 3, and 4 again. Which ones have inverses that are, put the word only above this. Which ones have inverses that are only a relation then? Number 2. Because do you realize that the green thing is not a function in the first place? It doesn't pass the vertical line test. It's a crazy thing of back and forth. It's like, when do you use the VLT? When do you use the HLT? When do you use the VLT? When do you use the HLT? Well, now let's answer that question. Let's realize that I'm going to give you a new note card. Orange note card time. If you haven't picked one up, come pick one up. Your orange note card is the same information as this. We are going to find the equation of the inverse of a function. It is pretty stinking easy. Honestly, I don't even think you'll need this orange note card on your test because the process is pretty stinking easy, except for what you write down if it doesn't. So here's what we want to do. Number 1, graph or draw a sketch of the given problem. Let's do that. Number 1, you need to think, what does this look like? Line, parabola, cubic, etc. Number 1, what does it look like? Now, not just some made-up line, whatever you want. Do you know the y-intercept of that puppy? So you don't need to use a straight edge. That'll take too much. If you want to, you can. Sketch yourself a little axis. Okay, it's just a sketch. Then y-intercept is -5, correct? Slope 2 over 1, 2 over 1, 2 over 1. Got my little sketch right there. Rough sketch. Rough sketch. Sound cool? So that's part 1. Graph or sketch the given problem. Then ask yourself this question. Does this thing pass the HLT? Yes or no? Yes. So, since we said yes, and we go right here, that means that the inverse is a function. Cool? Write down the domain and range for this puppy. So, we'll do it like so. D for domain. What's the domain of that thing? All reals, which is cool to say. Let's write it down like this. -infinity to +infinity. Anytime you say all reals, that's what we mean to write down, from -infinity to +infinity. How about the range? Low to high. What's the range of this thing? All reals, right? -infinity, +infinity. Everyone cool with that? Cool. We've done this. Then complete steps 2 through 5. Step 2, replace f of x with y. So now, here's the equation of this puppy right here. We're going to write its inverse equation. So it says replace f of x with y. I'll do that. That would be y equals 2x minus 5. Sound all right? Please holler if you have a question. You with me on that? Now we're going to do the inverse. Doesn't the inverse mean x and y change places? Correct? X and y are supposed to switch. So that's what step 3 says. Switch x and y around. This is a y, it becomes an x. This is an x, it becomes a y. All I did right there in that second thing was switch x and y around because we're taking the inverse of it. Just like you did in your table, didn't you switch the entire x column and the entire y column around? Next, solve for y. Go for it. Solve that for y. Add 5 to both sides, correct? Add 5 to both sides. Then divide everything by 2. I'm not a fan of doing the all over stuff. Some people that do this, y equals x plus 5 all over 2. I don't want you to do that. Right? I want you to divide each term individually by 2. Eraser, eraser, eraser. Is everyone cool with me solving this for y? Yeah? Step 4. We're going to do 2 things. One thing that this doesn't say is we'll use the symmetric property of equality to make these switch sides. Right, you all cool with that? Those can switch from left to right. And where there's a y, we're now going to replace it with this, f inverse. You have to be familiar with that in your trigonometry. Remember when you did sine to the minus 1, cosine to the minus 1, and tangent to the minus 1? Those are called inverse functions, right? That's an inverse that to the minus 1. So this is really f inverse of x equals 1/2 x plus 5 halves. Same thing we had right here. We just, where there was a y, we replace it with f inverse. This is the equation of the inverse. If I graph this, it's got a y-intercept of 5 halves, and it's got a slope of 1/2, so then we'd graph it. They want us to write the domain and range of this thing. It's so simple. Didn't we switch x and y around to do this in the first place? To write the domain and range of the inverse, you switch the domain and range around, right? The range will become the domain, and the domain becomes the range. So it's just the old switcheroony. It just so happens they're both all reals, so this is coming here. This is our new domain, and this is our new range. The range was the domain of the original function. Pulling the switch. Sound all right? Next one. Make yourself a little axis. Let's sketch a picture of him. Do you have the ability to sketch a picture of him perfectly right now in your brain? We could have done this one. It was a line. Everybody knows what that looks like. This, you do know what it looks like, but it could have some turning points in there, correct? Couldn't it do all that crazy relative max, relative min? So how could I see what this really looks like? What would you want to do to see what it really looks like? Calculator. Let's punch him in. Clear that guy out. Oh, it probably was what it was. Dang it, that's what it was. X to the third plus x squared minus 3x plus 1. Double check you got him punched in right. Zoom 6 him. Everyone with me? I don't give a darn about all the exact places, like where the zeros are, where this is, where that is. We're making a sketch of him. So over here, would you believe that the sketch looks like this? Y'all cool with that? But that was very important, because now we can look at that sketch and do the rest of this sheet right here. The rest of our orange note card says, all right, we made a sketch. What's the next thing we should check on that sketch? Does that sketch pass the HLT? What do you think, yes or no? What do you think? Does that pass the HLT? Nope, that went through 3 different places right there. So it does not pass the HLT. So here's what it tells us to write. The graph fails the HLT. Therefore, there is an inverse. The graph fails the HLT. Therefore, there is an inverse, but the inverse is not a function. Therefore, there is an inverse, but the inverse is not a function. Therefore, there is an inverse, but the inverse is not a function. And honestly, by the time we do enough of these, that's probably all you need the orange note card for. Is like, what's that thing I'm supposed to write down again? I haven't made up my mind if I'm going to let you use the orange note card on the test or not. So prepare like you need to memorize that, because I don't think we know that purple note card very well at all, because I let you use it on a test. Does that make sense? Like, we still don't really understand how to do transformations of graphs, which is coming up this chapter, BT dubs. Is everyone cool with that? Now, wait a minute. Will every cubic be a fail of the HLT? Because, I mean, look at the parent cubic right here. Rough sketch, but does that pass the HLT? So when it's something you're unfamiliar with, punch it into calculator, give me a rough sketch of what it looks like. Next. Interesting. Number 3. It's got a fraction in it. You got any variables in the denominator, though? Nope. What would that look like? Line, parabola, cubic, fourth power, any ideas? That's a line right there. I'm a big fan of doing this. 1/5 x minus 3/5 is really what that is. Just a little jot down of that's 1/5 x minus 3/5. Make me a sketch of that thing. That's a line. I'm not a guy that believes in that all over 5 until later. It's got a y-intercept of negative 3/5, so I know it's somewhere down here. Slope, rise 1, run 3. Rise 1, run 3. Rough, 1, 5, my bad. Whatever, same concept. Rise 1, run 5. Rise 1, run 5. It's just a rough sketch. Cool? What's the next question you ask yourself according to the orange note card? Does that graph pass the horizontal line test? Yay or nay? Yes. So give me the domain and range of that puppy. That's what the card tells you to do. The domain and the range. It's a linear guy. It's all reals all the way around. 4-step process. Now, I know it starts with a 2, but there's really only 4 steps in there. First thing we do is change f of x to y. And I am now going to keep it in this form. You'll see why. I'm going to keep it in this form. This is much easier to solve in this form than in that form. So I'm going to change f of x to y. I would get y equals x minus 3 all over 5. I'm going to keep it like that. What's the next move? Switch x and y. There's the inverse process right there. Switch x and y around. So this will become an x. That will become a y. Cool? And now it makes it tremendously easy to solve for y. You've got this minus 3 here, and I do understand you're like, aren't you supposed to like get rid of all that addition and subtraction? This is a group. We got to save that group for last. We're doing the order of operation backwards. Get rid of that all over 5 first. How do you get rid of that all over 5? Times both sides by 5. That would become 5x equals y minus 3. It just makes that all over 5 go away. Now what do you do to solve for y? Add 3. 5x plus 3 equals y. Fabulous. One more move. Switching the old y to turn out to be f inverse of x. So I got f inverse of x equals 5x plus 3. Then tell me the new domain and new range. It's the switcheroo on your original. The domain of the original will become the range of your inverse and vice versa. It just so happens that they're the same thing. 2? Yes, no, maybe? I pray that you do not need to punch the next one in the calculator either. It is a quadratic. Do you know what they look like? Parabolas. Open up or open down? This one opens up. Is it translated anywhere? Is it over to the right, any shifted down or anything like that? What do you think? Nope, not at all. All that this 3 does is it vertically compresses it. Skinnier, fattier, whatever, you know. Vertically stretched, vertically compressed. That makes it 3 times fatter. This would be translated 1 unit to the left because there was something inside the parentheses. This would make it go where? 5 units where? Up. Don't worry, we'll do more of that. And that's why I do not like the fact that you get that purple note card, because you still don't really understand it in the first place. So, there's a sketch of that. Do the horizontal line test. Does it pass the horizontal line test? Nope. So your orange card will tell you what to do. Every function has an inverse. This is a function. This thing itself passes the vertical line test. It does have an inverse. Its inverse would look like this. Right there. But that's not a function right there. Its inverse is not a function. We didn't even need to graph the red thing because we could just do the horizontal line test on the blue thing, which is equivalent to doing the vertical line test on the red thing. We wanted to know if the red thing was a function. Well, to check to see if you are a function, you do the vertical line test. To check to see if the inverse of somebody's a function, you do the horizontal line test. One more. 5. What does he look like? Line, parabola, cubic, 4th power. What is that guy? He's a line. Split him up so you can see what he really looks like. I call him 2x plus 3 halves. Right, 2x. 4 over 2 is 2. 3 over 2 is 3 over 2. Give me a sketch of him. Check my sketch out. Good or bad? That's bad. Why is that bad? That slope is what kind of slope right here? Negative. I want it to be positive, correct? Then try the whole process for yourself. Go through the orange note card, work with PAL if you want to, pause the video, get this problem done for me. Follow the orange note card. Yes, it passes the horizontal line test, so domain as follows here. Change the old f of x to a y, pull a switch, solve for y. I got this. Y equals 1/2 x minus 3/4. Got to change the old y to an f inverse though, and then the domain and range, pull the switch. Obviously they're the same thing, so you still write the same thing on that. This is how to get the equation of the inverse. On the next few problems, they want to know, are these two inverses of each other? And there's many ways to figure it out. The fastest way is to see if the composites of each other equal x. They want to know if f of g of x equals g of f of x, which equals x. It is so confusing sounding, but here's all you got to do. 2 things. You got to find f of g of x, and you also have to find g of f of x. If you get x back both times for your final answer of each one of those, that means they're inverses of each other. If you do not get x back both times, they are not inverses of each other. So here's what we will do. Let's do one thing at a time. This is the work I want to see. First thing I want to find, f of g of x equals. If I do f of g of x, and f is following g, which one really comes first? G. I want to put g into f. Here's g right here, correct? Let's put them into f wherever there's an x. doesn't this whole thing have to go in for x? You with me on that? So it would become this x plus 9, isn't that g, and then the rest of f is still minus 9 there. Does everyone see what it is right there? All of g went in for x into f, and there's still a minus 9. Then I'm going to come straight down and clean that up. What's that turn into? X. That's not enough. We're halfway there. One satisfactory thing. F of g of x turned out to equal x. Cool? Now we have to do the other way around. G of f of x. Cool? Let's see what g of f of x equals. G of f of x means we want to take f and put him into g. So I'm going to take the f guy, so I'll erase all my crazy markings. This f guy needs to go in to g. Wouldn't that be x minus 9? And then the thing that's still there is a plus 9. Correct? What does that clean up to be? X. Are those two functions inverses of each other? We got x back both times, so the answer is yes. And I want you to write this down. F of g of x equals g of f of x, which equals x. It's the rule for it. It's the two things that you had here. This equals this, which what did they equal? X. They all equaled x. Okay? Let's try the next one. They want to know if they're inverses. Order, I just do the same thing every time. I always start with fog, if you will. F of g of x. Please don't call that fog. F of g of x. G has got to go in to f, correct? So I make myself a little helper arrow, and I'll say that's 3 times 3x minus 5 plus 5. You see that the entire g function went in for x into those parentheses. Everyone good with that so far? I'm going to clean that up. That would be 9x minus 15 plus 5, which equals 9x minus 10. Right? That's enough right there to say that we can answer this question. Are these two inverses of each other? How come? What didn't we get? We didn't get x. It doesn't matter if I got a 9x minus 10 on the other guy. They got to equal x either time. So this one is a no. Okay? That's all we'll put. No.